This is lecture 20. So what we have here is quite a few actually, interrupt timing examples, and then we want to talk about switch balance and one-shots, and finally we'll do an example or two in this set of lectures. So this is the state diagram describing the state machine that controls the sequencing of instructions in the RISC-V. Now the notion is that instructions take 2 clock cycles each, except for a write back instruction it requires 3 clock cycles, and so the thing that's going to control it is this state diagram here. Now the issue, suddenly we're talking about interrupts, and that's going to complicated our original state diagram. And the notion is a couple of things. The interrupts, if I'm executing a non-load type instruction, I have an interrupt in this state, I go into the interrupt cycle. Otherwise I just go back to fetch. Even if I have an interrupt here and it's a load type instruction, I go to the write back state. Okay, and if that interrupt is still there, I will go into the interrupt cycle. So when an interrupt is received in this cycle here, or I'm sorry, in part of the interrupt cycle, the interrupt cycle is going to implement the interrupt architecture for RISC-V. So the interrupt architecture, 3 things happen when you get an interrupt. One is you load the interrupt vector address, which is the address of the interrupt service routine. You put it in the PC. You also take the current PC, which is already pointing at the next instruction, and you save that in a CSR register, control and status register. And this is essentially when I'm done with the interrupt. What I'm going to do is take that address in that register and put it back in the PC. You can see it down here. We'll get to that in a second. The third thing I'm going to do here is I'm going to mask the interrupt. I'm going to disable the interrupts by writing a 0 to this register here. Now, issue here is I can do all 3 of these things in one cycle. So anyway, let's look at this. When I'm returning from interrupt, what I'm going to do here is just take that return address I stored in this register, put it in the PC. So this is an example of an interrupt being taken. Here's my instruction here. By the way it's written, this is not a load type instruction because it only has a fetch and execute. But what we have here is interrupt turning on sometime, and it goes off sometime, not a big deal. But the important thing here, it is present at the end of the execute cycle for this non-load type instruction. At the same time, the interrupts are enabled. They're unmasked, and so it's going to go into the interrupt cycle, and that's what you see here. It goes into the interrupt cycle. As part of the interrupt cycle, it's going to set up those 3 things that happened before. One of those 3 things is it's going to set this address to be loaded into the PC. It's going to set the current PC to be loaded into the CSR register, and it's going to disable the interrupts. And that's it. So then after that point, it's normal processing starting at this instruction, and that's essentially some of the important timing associated with acting on an interrupt. Now, exiting an interrupt, very much simpler. Essentially, here's your return from interrupt instruction. It's a 2-cycle instruction. It's not even a pseudo instruction. At the end of the execute cycle, what I'm going to do here is take that address that's in this CSR register, which is the address of the instruction after the instruction that would have been implemented had I not taken the interrupt. So that's going to be my return address. I'm just going to stick it into the PC. So there's some issues when you start using interrupts in a real environment, and essentially this is the state machine here, and the idea here is the pulse can be too short and it can be too long. So if it's too short, it may turn on in the fetch cycle real fast and turn off in the fetch cycle. That may be a valid interrupt, but for this for the microcontroller to act on the interrupt, that interrupt has to be present during the end of the execute cycle or end of the write back cycle for a load type instruction. So if it's too short, you're going to miss it. If it's too long, essentially it could come back through this thing and have that interrupt still asserted and go back into another interrupt cycle for the same, essentially the same interrupt. So you don't want it too short, you'll miss it. Too long, you'll process multiple interrupts, which means you'll call the interrupt service routine multiple times for the same interrupt signal assertion. The other thing here is typically what we're going to do is connect the interrupt to a button. Now buttons or a switch, they're mechanical devices. You know, they have contacts. When you actuate the button or switch or deactivate it, the switches or the contacts bounce. They actually bounce no matter how soft you press the button. The contacts are going to bounce. It's totally weird. But anyway, so we have to deal with that also. So there's two ways to deal with bounce. And one is in hardware and the other is in software. So for experiment 8, which is coming up, we're going to give you the module to deal with in hardware. So the notion is that when you're going to zero, from a 0 to 1, for example, this is the example here, you think it does this, but what it really does is it bounces a couple times before it stays on. Okay, so what happens is you think it's turning on like this, but it's actually bouncing a whole bunch of times, and then eventually it arrives at a steady state here. Okay, so bouncing, certainly all switches have it as a characteristic of the switch. Typically what we want is this thing here, and so let's look at this thing. So I copied this out of a manual, the parts manual, the Jamco manual, and essentially here it is, a switch, and there it is. It says bounce time 10 milliseconds, and what that means is a little bit cryptic. It means after 10 milliseconds, the output of the switch is guaranteed to be stable, which means it will quit bouncing. It's guaranteed to be done bouncing after 10 milliseconds. Heck, it may not bounce at all, but what they're saying is no matter how much it bounces, it'll be done bouncing after 10 milliseconds. And so the issue here is all these little bounces here. This is on the millisecond level. All these little bounces here could cause their own interrupts to happen if you're connected to if the switch is connected to interrupt, and that's probably not what you want. Remember, the microcontroller is operating on nanosecond level. These bounces are happening on a millisecond level. It's going to be a problem. So what you're going to do is debounce it, clean it up. Your signal looks like that. The drawbacks are you're going to have to provide extra hardware if you do it in hardware, or extra firmware if you do it debounce it in firmware. And there's also going to be a delay. You think you press the button here, but it doesn't really get pressed until that time. Typically this is a little bit of delay you have to deal with one way or another. So once again, pulse width issues are very important. I've got two things going on here. It could be too short or too long. If it's too short, your state machine is going to miss it. If it's too long, if the pulse is too long, the state machine will come back and see that same interrupt again and go right back into a interrupt cycle, which is probably not what you want. So the other issue here is to control the length of the pulse is we're going to put it into a one-shot. Okay, so what we want is ensure that it gets caught, the interrupt gets caught, but ensure that it's gone before it can be caught a second time. And so essentially we're going to tie it to a one-shot. So we're going to take this output here and put it into a one-shot. A one-shot is just simply a device that is going to filter this thing. Now, this is what the input looks like. We'll say in, and this is what the output looks like. meaning that this state here, this pulse width, is kind of not stable. So it's only going to be in this or in this unstable state for a given amount of time, and typically it's controllable. And so that the pulse width is usually programmable, not a big deal. So that means we can make it long enough and make it short enough. So one shot is our key to success on this. And we'll, the fun slide here is a one shot is also known as a monostable multivibrator, because monostable, here's your one shot, it has one stable state, which is the off state. It's only in this state temporarily after it gets like a rising edge or something like that. So trivia question, astable multivibrator looks like this, which you know is an oscillator, which is a clock signal. And a bistable multivibrator has two stable states, which is you should know as a flip-flop. Okay, you'll probably never hear those terms again, but just in case you do. So it becomes a really important issue. A couple of things here is how fast you can enable the interrupts after you take an interrupt. And this is important because it has to do with the pulse width. And certainly I don't want to re-enable the interrupts until that interrupt pulse is gone. That's the key. So I want to know how possibly fast that can be. Other thing here is I want to know officially the minimum time required for an interrupt to that interrupt pulse, such that the state machine catches it. But I want to also know keep it short enough that there's no possibility whatsoever that I could ever have that interrupt still there by the time I'm done processing my interrupt service routine. So here's our diagram here, and what this one is showing is how fast I can get those interrupts re-enabled. Okay, so here's an instruction. Here you got your interrupt coming in here, turns off here, great. You go into the interrupt cycle, etc., etc. This is the same, mostly the same picture as before, but I'm going to say this is the address of my interrupt service routine. The first instruction re-enables the interrupts. Not something I'd really want to do, but for this problem, we're just going to talk about it. So that means the first instruction in the interrupt service routine, I re-enable interrupts, which means I'm going to turn the CSR write signal on down here, and that's going to write that value into the register. So life is good on that one. The result is, remember the interrupts are disabled automatically in hardware. This instruction re-enables them. So you can see that pulse width is going to be 2 clock cycles long. And so that's the answer to our first question. And so I think I have a clean slide here. Okay, here's a clean slide. And so we want to know what's the width of the pulse to guarantee that the interrupt is always caught. Now, so that means worst case scenario is I'm gonna scribble this out and pretend it's not a interrupt cycle, but it's a write back cycle. So if this interrupt turns on right here, I need that to be present at the end of that write back cycle, which I want to be able to catch that right there, which means I have to have it at least up until that point right there. And so you can see very clearly that to guarantee in all situations that I'm going to catch that interrupt, it needs to be 3 clock cycles long. So the other question is, I'm going to go ahead and erase this, is the notion that well, how fast can I turn these off? So the idea is, and we'll go through this. We'll pretend like this is we'll pretend this is a load type instruction. So this is going to be pretend. Okay, this is going to be 3 clock cycles. Well, this is 3 clock cycles, and then you got an interrupt cycle. That's 1, and then for some strange reason I turn my interrupts on. First instruction in interrupt service routine, that is 2 more clock cycles, and now my interrupts are enabled, so I better have that pulse gone by the end of this cycle right here, which is essentially going to be 2 more clock cycles. So the maximum that that you could make this pulse, and not the maximum, but you just don't want it longer than 8. If it's longer than 8 clock cycles, there's a chance it may execute the same interrupt service routine again. So once again, worst case, 3 clock cycles, roughly speaking, for a load type instruction, 1 clock cycle for the interrupt cycle, 2 clock cycles for the instruction that re-enables the interrupts, and then I want it gone by the end of the next instruction, which could be any instruction, but I want it gone before it completes the execute cycle. So the answer essentially is 8. But the real key to this is 3 clock cycles is ideal. You want to make that pulse width 3 clock cycles, and that's, if it's 3 clock cycles, it's always going to be caught, and it will never be caught twice by the state machine.